In this video, we're going to be discussing some science known as kinetic molecular theory. Kinetic molecular theory uses some very basic physics to come up with some very good explanations for some very complex chemistry. We'll start by going over a couple learning objectives. We'll start with a discussion of what kinetic molecular theory is all about. By the way, you'll notice we very often use these abbreviations KMT. It's a lot of letters to write. This makes it a lot quicker. Kinetic molecular theory is ultimately based on a series of 6 postulates, and these postulates basically define the characteristics of particles in a sample. These postulates then will start providing us with an explanation for the different properties of gases, things like pressure, temperature, volume, and the number of gas particles that are present. Finally then, once we get the idea of what these individual properties are, we'll use kinetic molecular theory to link them all together. How does pressure change when I change one of the other characteristics? We'll start then with a basic discussion of what kinetic molecular theory actually is. In general, it's a theory that tries to approximate the behavior of a large number of individual particles. So we're trying to predict what the particles are doing. And the ultimate goal then is that this will allow us to explain the behavioral properties of the entire sample. The philosophy is we know what the particles are doing, then we should understand what the sample as a whole is doing as well. A quick translation, because that definition is a little bit technical. Substances are made of very large groups of particles, so it's always made of millions upon millions upon millions of particles. The particle behavior in these large groups can be predicted very quickly and easily with some very simple physics and some very simple statistics. Since the numbers are so large, we can treat them as a whole statistically, even if we don't know what each individual particle is doing. And the idea then, the ultimate goal, is that if we understand the behavior of all of those particles, then we should also understand the behavior of the sample as a whole. If we know what the atoms and molecules are doing, we'll know what the whole tank of gas is doing. Now, as we've already kind of alluded to, primarily kinetic molecular theory has a lot of applications. Mostly we speak of it in terms of behaviors of gases, but kinetic molecular theory can also be used to describe the behaviors of solids and liquids. However, when we do use it in that context, we have to modify it a little bit. The thing that changes are those rules, those postulates that I mentioned on the previous slide. So that brings us then right to the important part of the video here. What are these rules? What are the guidelines set down by kinetic molecular theory in order to explain what those gas particles are actually doing? We'll go through them one at a time. Ultimately, there are 6. Once we've gone through the 6 of them, we'll then talk about how they apply to the behavior of individual gas particles. The first postulate of kinetic molecular theory is that gases are made of large numbers of very, very small particles. And I can't stress the term large, and I can't stress the term small enough here. We've already talked a couple times in the year that particles, atoms, and molecules are incredibly small, usually a lot smaller than most people realize. And the numbers of them in any given sample are extremely large. This allows us, again, to treat these particle behaviors statistically, so we don't have to know what each individual particle is doing. The second postulate of kinetic molecular theory is that these particles have a mass. Regardless of how small they are, they still have a mass, which means when they interact with one another, when they collide with something, they exert some forces. If you recall, that kind of alludes back to some physics in previous chapters we've talked about, or previous subjects I should say, F equals ma. But we'll get more into that a little bit later. These particles are in constant, rapid, random motion. Particles of gases and particles of all substances are always moving, and they're moving at very, very high velocities, hundreds of meters per second. So much, much, much faster than anything we need, or anything we're normally used to dealing with. The collisions between particles and tank walls are completely elastic. And if you forget from your physics courses what that means, completely elastic means no loss of energy. So whenever these collisions occur, there's no loss of kinetic energy in the process. Energy can be transferred from one particle to another, but there's no losses due to friction or resistance of any type. So these particles are moving, and they will continue to move indefinitely. Our next postulate, number 5, then, is that the temperature of a gas is proportional to the average kinetic energy of all particles. And this is going to be one that's going to be very, very important for us. Average kinetic energy, in most cases for us, is going to translate into velocity. So basically what we're saying here is as the kinetic energy of our particles increases, the average speed of our particles are going to increase, and that's all correlated back to temperature. Last but not least, our sixth postulate is that there are no attractive or repulsive forces between molecules. Now I'm going to start out by saying that this is not true. There definitely are attractive forces and repulsive forces between molecules. But these attractive and repulsive forces are very, very weak. To make the mathematics with kinetic molecular theory much simpler, we can ignore these attractive and repulsive forces and we get answers that are pretty reasonable even if they're not exact. Later in the video and later in class, we'll talk about the fact that we can use this postulate sometimes and other times we cannot, depending on the gas sample we're dealing with. And this will be the difference for us between an ideal gas and a real gas. Ideal gases have no attractive and repulsive forces. The math is very simple. Real gases do have attractive and repulsive forces, and unfortunately the math gets a lot more complex. So we're going to hold off on getting into the postulates any more than that for now, and we're going to turn instead to talk about the properties of gases that we can actually measure and quantify. The first of those properties is something that most people recognize pretty quick and easily, and that is pressure. A quick definition of pressure, probably a little more technical than you're used to, is the net force a gas exerts on a surface, and that force is exerted per unit of area of surface. There are many, many, many different units of pressure out there. Pounds per square inch is something we use a lot here in the US. Atmospheres, pascals, bar, torr, millimeters of mercury are other units that have come along in context of different things. The one we're going to focus primarily on here in this year is this guy right here. We'll be measuring a lot of our pressures in atmospheres, and we'll get into that unit a little more later on. Our next property we'll be dealing with is the volume of the gas. The volume of the gas is actually very strange. We talked about this in previous videos. The volume really is determined by the size of the container that the gas is within. If you put the same amount of gas in a small little vial and you put the same amount of the gas in a giant room, the gas will always fill its container. The unit we use to keep track of the volume of gas is liters, the same thing we keep track of the volume of liquids with. And this volume can be measured and thought of, I guess, in two different ways. It can be thought of as the space between the gas particles, and if you're only worried about the space between the gas particles, again, this is that difference we're talking about where you're dealing with an ideal gas. It's not a real way of getting an idea of what the gas is doing, but it's a very, very close approximation. If you consider the space between the gas particles and the volume of the particle itself, that's where you start moving into the world of real gases. It's a different way of keeping track of things. A lot more data is needed, but you get answers that are a little closer to the real things. And you can start to see why this difference is not such a big difference in most cases. The volume of the gas particle itself, it's an atom. It's super duper mega tiny, and it doesn't change the volume measurement that much. But if you're dealing with certain situations or you need very, very accurate numbers, this can be the difference between right and wrong answers. Continuing our discussion of properties of gases, there's two more we need to worry about. The amount of gas present, the symbol of which is the lowercase letter n, is simply a count of the number of gas particles in your sample, and we keep track of that with the unit of moles. So how many moles of gas particles do we have? Last but not least, that brings us to the temperature of a gas. We use the capital letter T to keep track of temperature. And as we've already mentioned in our postulates, temperature is really a measurement of the average kinetic energy of your gas particles. The unit we use to keep track of temperature is Kelvin. We brought this up earlier in the year. And the equation, just because we need to do this conversion a lot, the equation for converting into Kelvin is simply to take the temperature in degrees Celsius, and pardon my typo here, and we need to add in 273.14. So it takes the Celsius scale, shifts it over 273 degrees, and now we have a temperature in Kelvin. Now that we've identified the postulates of kinetic molecular theory, now that we've identified the main characteristics about a gas that we can measure, we can start talking about how these gas particles are, or how the properties, I should say, are related to one another. To do this, we're going to be using something known as a gas law simulator. If we really had the time and the resources to do it, we could get a real tank of gas and start tinkering with pressures and temperatures and volumes and see how they changed one another. But that kind of work is very difficult and requires very specialized equipment. Instead, we're going to be using some computer software that simulates gas behavior, and we'll be able to make our measures and relationship approximations using that. The simulator works very simply. It uses the postulates of kinetic molecular theory to simulate the behavior of gas particles in a small tank. Basically, we're using a physics engine here. We put in some characteristics, we put in some particles, and then we let the physics do its job. We let kinetic molecular theory do its job, and it starts making those gas particles behave like real gas particles. The simulator then allows us to adjust things like pressure, volume, the amount of gas, and the temperature very, very easily, which allows us to see a couple different things. First of all, it allows us to see when I change temperature, what effect is it going to have on my other variables, so we can find those relationships. And it also allows us to see when I change temperature, how are my gas particles going to start moving around or behaving differently. So we're going to see the things happening at the atomic level with kinetic molecular theory and things happening at the sample size level. So it allows us to see a pretty global picture. This particular simulator that we're going to be using is available online as a Java applet. It was created by some scientists over at Oklahoma State University. There's a link on the bottom of the page if you'd like to play around with yourself. It can be kind of fun to play with, and as you'll see in a minute, even a little bit mesmerizing once you start staring at those gas particles for too long. What's going to happen next is we're going to open up the simulator. I'm going to start talking about the different characteristics, relating them back to the postulates. I'm going to go through the simulator first, and then we'll come back to a slide that kind of summarizes the information we come with. Ultimately, we're going to walk away with relationships between pressure, volume, number of moles, and temperatures. And later we'll use those relationships in class to start developing some equations to allow us to mathematically relate these together. So here's our first look at the gas loss simulator software. There's a couple different things we need to be aware of when we're playing around with this. First of all, here is our actual sample tank, and we can see inside our sample tank we have our moving gas particles. Up here in the top of the screen we have our properties that we can deal with. The pressure of our gas, the volume of our gas, the amount of gas present, and we actually have two gases that we can work with here, helium and neon, and finally the temperature of our gas. We're going to play around with this and see how changing one of these variables goes back and affects the pressure of our sample. So the first relationship we're going to look at is going to be the relationship between the temperature of the gas and between the pressure that it happens. As you recall from before, temperature is proportional to the speed of the molecules, and what you can see here is that as I change the temperature of my gas sample, we see the velocity of our gas particles changes as well. When the temperature is low, they move very slowly. When the temperature is high, they move much quicker. Now what I want you to notice here is that as we move the temperature from a high temperature down to a low temperature, it's having an effect on the pressure of our gas. When the temperature is low, the pressure is also low. When the temperature is high, the pressure is also high. This shows us that there's a direct relationship between pressure and temperature. Now, as I move the temperature around and you watch instead of the properties, the gas particles themselves, when the temperature is low, our gas particles move slowly. When they're moving slowly, it takes them a longer time to reach the walls of the tank. And when they collide with the walls of the tank, they collide at much slower speeds. The end result is each of those collisions happens less frequently, and each of those collisions is softer, and as a result, the net outward force or the net outward push on the actual walls of the tank of itself is going to be lower. As our temperature increases, we can see the particles move faster, they hit the walls more frequently, they hit the walls harder. As a result, that net outwards force is going to get stronger and stronger. So now we've identified a direct relationship between pressure and temperature. So we've just had a chance to look at the pressure-temperature relationship using our gas loss simulators, and we saw as the temperature changed, it affected our pressure as well. The take-home message from this that we can say is that pressure is directly proportional to the temperature of our gas sample. As temperature goes up, our pressure goes up as well. And we can make a little mini equation here saying that the pressure of our gas is equal to the temperature of gas times some unknown constant. We'll worry about that unknown constant later on. But what we're going to see with this formula is that any equations we make with this, with these relationships is going to have to match this to some extent. It's going to have pressure going up and temperature going up at the same time. To explain why, or at least to put it into some text of what we already talked about, higher temperature means a couple different things. First of all, it means faster moving particles. Temperature is correlated to average kinetic energy. Those faster moving particles are going to collide with the walls more often, and those faster moving particles are going to collide harder with the wall. If you recall from last year, this is the impulse momentum theorem. If we're moving faster, when we collide with the wall, our change in velocity is going to be greater, and as a result, the force that we exert on that wall is going to be higher as well. So we can see this very simply mathematically. This ultimately means more force being exerted on the walls, and it ultimately means a higher pressure. So we can clearly see as temperature goes up here, because of all these ideas, we're going to see our pressure go up as well. The next relationship we'll look at is going to be the relationship between the amount of gas present and the pressure of the gas. Again, amount of gas is denoted by the letter N here. We're going to work only with our moles of helium. As I move the slider to the right, we can see that there are more and more particles in the tank. As I move the slider to the left, we can see that there are fewer and fewer particles in the tank. When looking at the properties themselves, we can see that as the number of moles of helium gas increases, the pressure of our gas increases as well. When the number of moles of helium decreases, then the pressure decreases. So we can see here, just like before, there's a direct relationship between the number of moles of gas present and the pressure of our sample of gas particles. In terms of explanations, it goes back to collisions again. When we have more particles in the tank, the number of collisions with the walls of the tank are much, much higher. They're much, much more frequent. As a result of being more frequent collisions, there are more forces exerted on the wall of the tank, and as a result, the pressure goes up. When there are fewer particles, there are fewer collisions, there are fewer outward forces pushing on the tank walls, and the pressure of our sample drops. So again, we've now identified that there is a direct relationship between moles and pressure, and we've also come up with an explanation in terms of kinetic molecular theory as to what that explanation is. All right, we've had our second look at the gas law simulator, and what we discovered the second time around is that pressure is directly proportional to the number of gas particles present. So again, here's our second big relationship that we can draw between the different properties of a gas. If you want to start talking about this a little more mathematically, as the value for number n goes up, we see pressure go up as well. And again, we can see this in equation. Pressure then, in any equation we use, is going to have to be equal to some constant value times the number of moles. That way, as this value increases in our formula, our pressure is also going to increase in our formula. The final equations we eventually get are going to be different than this, but they have to match this to some extent. To put our explanation down on paper, more particles in our gas sample mean a couple different things. Again, if there are more particles present, we would expect to see more collisions with the tank walls. Those more collisions mean a larger total force being exerted on the tank walls, and ultimately, again, it's going to mean more pressure. So just as we already said, we're going to get more particles proportional to more pressure. As one goes up, the other has to go up as well. Our last relationship that we're going to be looking at in this case is going to be the relationship between the volume of our sample and the pressure of our gas. We can see here again, I can change my slider. As I move the volume up, we can see the size of our tank increases. As I move the slider down, we can see the size of our tank decreases quite dramatically in this case. You can also see as I move my slider back and forth that as the volume of the tank gets larger and larger, my pressure gets smaller and smaller. And as the volume of the tank gets smaller and smaller, the pressure inside of the tank gets larger and larger. So in this situation, we've identified the fact that there is an inverse relationship between volume and pressure. As volume gets big, pressure gets small. As volume gets small, pressure gets big. Again, the explanation for this comes in terms of collisions. When the tank is large, the particles have a larger distance to cover. They hit the tank walls less often, and as a result, they exert forces on the tank wall less often. Less forces means lower pressure. When the tank is very, very small, when the volume is low, maybe we'll get a little bigger than that. When the volume is very, very low, the particles have nowhere to go but hitting the tank wall, and as a result, they hit the wall more frequently, and the result is the force they exert happens more frequently, and the pressure increases. So again, we've identified that there's an inverse relationship between pressure and volume, and we've explained that in terms of kinetic molecular theory. We've now had a chance to look at our last relationship between pressure and a property here. In this case, it's going to be pressure being related to volume. And our statement we were able to derive from the previous run-through with the simulator is pressure is inversely proportional to the volume of a gas tank, which means that as the volume of our tank goes down, our pressure in this case goes up. Again, we can make a generic formula to match this. In this sense, again, C is a constant, and we can see here as the value of P goes up, the value of, and again I apologize here for a little typo, the value of V has to actually decrease. And likewise, if V goes down, pressure has to go up as well. So these guys move in opposite directions to one another, hence the inverse relationship. Again, to put on paper the explanation for this using kinetic molecular theory, a larger container, which is a larger volume, means a couple different things. First of all, it means more time between each collision with the tank wall. The particle has farther to travel before it finds a wall, and this ultimately results in fewer collisions. As we've already talked about, those collisions are forces exerted on the tank wall, which means the total force on our wall is going to be lower, and as a result of that, we're going to expect a lower pressure as well. So again, we can relate these two together. As our tank gets larger, our pressure is going to get smaller. So that's it in terms of our relationships. In class, we're going to take some time and pull all this together into some equations that we can use. But for now, the things you should be able to do are listed below. First of all, in terms of kinetic molecular theory itself, you should know what the theory is, what it's really based on, and you should know the 6 postulates. I don't expect you to be able to tell them to me word for word, but you should be able to describe them all very generally. You should also understand now the 4 different properties of a gas that we measure. You should be able to define each, you should know the units and symbols that go along with each, and you should be able to relate each one of them to kinetic molecular theory. How does pressure get explained? How does volume get explained? Etc., etc. Last but not least, we came up with scientific explanations for the relationships between pressure and the other 3 variables. You should be able to basically use those explanations in terms of kinetic molecular theory to explain why those things change in relation to one another. In class, like I said, we're going to pull all this together. We're going to make this into a couple formulas, and ultimately this is going to produce for us some mathematics that we can use to calculate pressure, volume, amount of gas, and temperature in any gas sample.